Assalamu alaikum students, this is our second lecture for the week 1. So previously we have discussed a simple vapor compression refrigeration system, all its components and how does it work, and we did an example numerical on that one. So now we are moving on to a multi-pressure system, a system which has not just one pressure, not just two pressure, that is one condenser pressure and one evaporator pressure, but now it will have one condenser pressure and maybe two or maybe more evaporator pressure. So it's called multi-pressure system. So the simple vapor compression system that has been dealt with is a two pressure system, one low side pressure which is the evaporator pressure and one high side pressure which is the condenser pressure. The performance of a single stage system shows that these systems are adequate as long as the temperature difference between the evaporator and the condenser, which is called temperature lift, is small. That is around minus 15 degrees generally, to minus 15 degree to minus 25 degrees centigrade is the temperature that they can produce, the lowest temperature it can produce. But what if we need a higher temperature lift, that is temperature lift of the range of minus 40 degree, or maybe in a chemical industry where cryogenic is being produced, or liquefaction of gases is required, where the temperature required, the lower temperature required maybe minus 150 degrees centigrade. Then how can we utilize this vapor compression system, or what modification we have to make it to achieve such a large temperature lift in it. And there are also cases where we just don't need one lower temperature, but we need more than one lower temperature. For example, in a dairy industry, you will need one evaporator to work at minus 35 degrees centigrade to make the ice cream or to harden the ice cream, and another evaporator to operate at 2 degrees centigrade to cool the milk. So ideally this can be achieved by employing two independent systems, which is however not desirable because of the higher cost, higher initial cost. As the temperature lift increases, the single stage system becomes inefficient and impractical. How it is inefficient, I want to explain you that one. So here I have a simple vapor compression system with I'm just modifying the evaporator pressure in it and how it changes. So if you look at this, there is two diagrams on your screen right now. One is the temperature entropy diagram, another one is the pressure enthalpy diagram. So we want to discuss the effect of decreasing evaporator temperature on the performance of your refrigeration cycle. So it can be seen from the TS diagram that for a given condenser temperature, the condenser temperature we are keeping it same, just changing the evaporator temperature. As the evaporator temperature decreases, throttling loss will increase. So as we are lowering the evaporator temperature, we are lowering the evaporator pressure basically. So it's the throttling loss will increase. Before we had the cooling capacity or the cooling produced is 1 to 4, now it is 1 to 4 dash. So it has been reduced. If you look at the area under 4 to 1 or 4 dash to 1 dash, you can see the 4 dash to 1 dash area under this line, the area has reduced. So the cooling produced by this one is reduced. And then if we go further down, there will be further throttling loss, so it will be reducing. So that's one of the loss. The superheat loss increase on the compressor side. If you look at before at state 1, it has to compress from here to point 2, but if we lower the evaporator pressure, now it has to go from a lower pressure to a much higher pressure, so a much higher temperature it has to go, and then this heat has to be rejected in the kitchen environment before it comes to the saturation, and then and then it will be losing this much heat. So initially we have to, the compressor has to work, we have to supply the compressor extra energy to compress it, and then we have to, the energy we have supplied to compressor, now we have to waste it because we don't need this extra heat that we get. So there is a superheat loss increase also. The compressor discharge temperature increases, of course, as the compressor starts from the lower, it has to go to the higher temperature. So the temperature will the temperature, outlet temperature will increase. The compressor's outlet temperature will increase. The quality of the vapor at the inlet to the evaporator increasing. So if you look up, this is 4.4 is the inlet to the evaporator. The quality, as we are moving, we know that the quality is 0 here and 1 here. 0 means no vapor, 1 means all vapor. So the quality is increasing as we are going further down on the evaporator pressure. So what does that mean? That means that we are getting more gas phase or more vapor phase at the inlet of the evaporator. And as we know, the vapor, you cannot expand it further. If it cannot be expanded, then it cannot absorb further heat from the evaporator surface. So it is just useless. It will just pass through the evaporator and go to the compressor, and then we have to compress it back to the high pressure. We will get it. We are dropping that vapor at a lower pressure and not getting any benefit out of it, and then compressing it back to the high pressure. So that will be a loss as we are going down to. So quality of the vapor at the inlet to the evaporator increase as a result of that. When we are lowering the evaporator pressure, specific volume at the inlet to the compressor will increase. So if you look up the specific volume of state 1, 1 dash and 1 double dash, the specific volume is increasing because we have more and more gas here. So as a result, the compressor has to work higher to compress it and send it back to the condenser pressure. So these are the losses which you will incur if you just try to modify your simple 4-component vapor compression system. So what to do? We want to introduce probably one more device. We are going to work with the 2 different ideas here. See, in a multi-pressure system, when we are modifying our simple system to a multi-pressure system, then in that case 2 or more low side pressure may be there. As you can see, we will need not just 1 evaporator pressure, we might need 2 evaporator pressure, 1 low pressure evaporator, 1 high pressure evaporator, or 1 low temperature, 1 high temperature evaporator. And often it will have provision for flash gas removal and intercooling. So we are going to add 1 more device into our regular vapor compression refrigeration system, that is, we call flash gas, flash tank. We call it flash tank to remove flash gas. What is the flash gas? Flash gas is the gas or is the vapor that we get when your saturated liquid from the outlet of the condenser goes to the expansion valve, and as it is traveling towards the evaporator, in between some of the liquid, the saturated liquid, will convert to gas before it reaches to the evaporator inlet. So that is the flash gas, and that gas will not do any benefit in producing the cooling. It will simply go to the evaporator, and then it has to pass through the evaporator and go to the compressor, and it has to be compressed. So that is what we are calling flash gas, and it is undesirable. We want to somehow take it out before it goes to the evaporator, so that we don't have to recompress it again and spend our energy without getting any benefit from this flash gas. And intercooling. So now as the pressure has been increased between the evaporator and the condenser, so we are going from a very, very low pressure to a very high pressure. So when we compress it, when we compress a vapor, or when we compress the gas, its temperature rises, and as the temperature rises, the amount of energy required to compress the gas becomes higher and higher and higher. So instead of compressing it in just one stage from 1 low pressure to a very high pressure, we want to compress it to a middle range, then send it to a heat exchanger, cool it down, and then compress it again. We will discuss it again in detail in the slides coming up. So flash gas removal, a saving in the power requirement of refrigeration system results if the flash gas that develops in the throttling process between the condenser and the evaporator is removed and recompressed before complete expansion. So we don't want this gas to go directly to the evaporator and then go to the compressor and then compress it back again from a very low pressure to very high pressure. Instead, we want to remove the flash gas in between, send it to a middle compressor, and then compress it back to the condenser. So that's the idea. When saturated liquid expands, through an expansion valve, the fraction of the vapor or flash gas progressively increases. The expansion process shown on the pressure enthalpy diagram in the figure below takes place from 1 to 2. The state point, as the expansion proceeds, moves into a region of a greater fraction of vapor. So as we are moving, the fraction of vapor is increasing as we are going from condenser to the evaporator. So this is initially this is where our condenser is. So, and this is our evaporator. Point 2 is the evaporator. So if we go straight expand from 1 to 2, then we are getting a lot of flash gas, which will do nothing. It will just simply come to the evaporator, pass through this evaporator, and then we have to send it back to the compressor and compress it back to state 1. So instead of doing that, what is being suggested is to separate this flash gas up to 0.3, up to the middle range 0.3, and then remove the vapor from here and send it to another compressor, maybe which is located at 0.6, and the remaining liquid should go to the evaporator at 0.2, and this can be further expanded. So here we are splitting at 0.3, we are splitting the saturated liquid and the saturated vapor. So vapor will be sent to either sent to a compressor here, or it can be sent to a tank. It can be collected into a tank. So this is that flash tank. So vapor from 1 to 3, it is coming here. The refrigerant will come in at 0.3. At 0.3 we install this flash tank. So it will be coming here at the flash tank, and then gas or the vapor will be going to 0.6 right here into a compressor, and the liquid will go to the expansion valve to evaporator. So the liquid will go, this point state 4 is the saturated liquid, it will go to the evaporator from here. So at 0.3 we are splitting it, we are splitting the gas and the liquid. So gas will go from the flash tank, it will go first into the flash tank, and from flash tank to a compressor at 0.6, and the liquid will go to 0.4, then expansion valve, and go to the evaporator. So that's the idea. That's this flash gas, flash tank will perform as a flash gas removal system. So flash tank for removing gas during expansion process. This is what going to happen. So inspection of the expansion from 6 to 7 confirms that it is wasteful. As you can see, 6 to 7, if we use just one compressor, then we have to, again from this point we have to expand it down to 7, because our compressor will be somewhere here with the evaporator. So it will be again wasteful. It will expand it, but we will not get any benefit out of it. In the first place, the refrigerant 7 can do no refrigerating. In the second place, work will be required to compress the vapor back to the pressure it had at 6. Now if we drop this vapor refrigerant to 0.7, we will be reducing the pressure, and then we will be compressing back to state 1. So it's a wasteful. Why do that? Why not install a compressor right here which will compress it back there? So that's the idea we are discussing. Why not perform part of expansion, then separate the liquid from the vapor, continue expanding the liquid, and recompress the vapor without further expansion. The equipment to achieve this separation is called a flash tank. The expansion from 1 to 3 takes place through a float valve, which serves the further purpose of maintaining a constant level in the flash tank to recompress the vapor at 6. A compressor must be available with the suction pressure of 6. Thus 2 compressors are needed in the system. So now we are thinking of employing one compressor at 0.7 and one 0.6 and one compressor at 0.6. So instead of one compressor, we can go for 2 compressors. The flash because we want to separate the gas or the vapor from the liquid. So we make it the tank, and this is the float valve. Float valve will maintain a certain level of the liquid in this tank, so that there will be continuous supply of liquid in this way. Otherwise, maybe when you are getting the refrigerant here, maybe there will be not enough liquid refrigerant available for this expansion valve or for this evaporator. So for that purpose, we maintain a level here with the help of a floating valve. So it will control how much liquid can come here. If the liquid refrigerant is too much, then this valve can close automatically with the help of this ball valve. And if it is less, then it will keep it open and the liquid will keep coming. And then the gas will evaporate from here and it will go to the compressor, to the high compressor. To separate the liquid from the gas, the velocity of the gas which is moving up should be very small, and that is what mentioned here. It should be around 1 meter per second. So normally vapor velocity is less than 1 meter per second will provide an adequate separation. This velocity is found by dividing the volume for flow of the vapor by the surface area of the liquid. The most efficient way to remove flash gas would be to separate the vapor continuously as it forms and to recompress it immediately. No practical means has yet been developed to accomplish that. So the best thing would be to just keep separating the flash gas from here and keep compressing it. We cannot do it. So that is why we need this flash tank. So with the liquid, the gas can be also collected here and then sent to the compressor, to the high pressure compressor. Now this this is minimizing the compressor work. Now we are going from a very low pressure evaporator pressure to a very high pressure, which is the condenser pressure. So should we go in one stage or in multiple stage, which will be the more beneficial? So this minimizing the compressor work idea we have discussed in thermodynamics before. I have just copied it here. As you can see, the reversible compressor work can be given by V dP. V is the specific volume and dP is the pressure difference, and kinetic and potential energies are negligible. So we can integrate this one to find out the work required by the compressor. So this will be the isentropic PV to the power k constant work. We can integrate here, and then this will be the answer. So if we use this is this one isentropic, and this one is polytropic, and this one is the isothermal work required. And if you look at these three lines, one of them is isentropic, polytropic, and isothermal. And the area under these curves on the left hand side, these areas are the amount of energy required by the compressor to compress it. So as you can see, the isentropic work is the highest work required, and polytropic is the second one, isothermal is the best one. So if we can compress the gas going from state 1 to the final state 2, from P1 to P2 isothermally, that is without increasing its temperature, then we will have the lowest amount of energy required by the compressor. But as you know, we cannot do that. As we are compressing the gas, its temperature will rise. So we want to use we want to mitigate this thing by intercooling, by providing a cooling heat exchanger here. So we will see that. Here is the idea: multi-stage compression. Instead of a single stage compression, we are doing a multi-stage compression with intercooling. So for what we do, this is our isothermal line, that which we cannot achieve. So we start from here, we compress it to a middle pressure, which we don't know right now, Px, and then we use a heat exchanger to cool it back to the same temperature here at state 1, and then compress it again. So if we had compressed it straight from point 1 to point 2, then this green solid line would have been followed. But now, as we are using a heat exchanger, so it will go to middle stage, then cooling again, then compressing again. So this shaded area is the amount of work that we have saved. how to achieve this, how to find out this pressure, the middle pressure. So for that we have added the compressor work in compressor 1 plus the compressor 2 work together. So these are the isentropic equation for the two isentropic equation for the two right here, or rather the polytropic one. So actually the polytropic equation it will follow, and then we take the find how to find the minimax. So take the differential with respect to the pressure and equate it to 0, then we get this equation: Px is equal to P1 P2 raised to the power half, or it will be Px upon P1 is equal to P2 over P1. To minimize compression work during two-stage compression, the pressure ratio across each stage of the compressor must be the same. So in this way we can figure out what is the Px value. If we know P1 and P2, we can find out what is the middle pressure is. P1 is generally the inlet pressure, evaporator pressure, which we normally know, and P2 is the condenser pressure, which is normally given. So with the help of this equation we can find out what is the middle pressure. So this is the same concept again. Intercooling idea. The intercooling between the two stages of compression reduces the work of compression per kilogram of vapor. In two-stage compression of air, for example, an intercooling from 0.2 to 4 as shown on the pressure 0.2 to 0.4 intercooling, okay, 2 to 4. It will save some work. This area representing the saving of the work. Now on figure 3b, which is this figure, shows how compression with intercooling appears on the pressure enthalpy diagram. So compression with intercooling, go from state 1 to state 2, then intercooling, then go to state 5, instead of going from 1, 2 to 3 straight here. So in that case the work required by the compressor will be higher. Instead of doing that, we go this way, so then the work required will be lower. Process 1, 2, 3 and 4, 5 are on the lines of constant entropy, but process 2, 3 falls on a flatter curve than process 4, 5 between the same two pressure. Therefore process 4, 5 shows a smaller increase in enthalpy, which indicates that the less work is required. Less work is required. So this enthalpy down here, from this enthalpy will be higher than enthalpy of 0.3 will be higher than the enthalpy of 0.4. So we will get a lower enthalpy if we follow 1, 2, 4 and 5 instead of going 1, 2 and 3. So that's the idea. This is how we can save the work. So intercooling in a refrigeration system can be accomplished with a water-cooled heat exchanger, as in figure 4. This is figure 4a and this is 4b. So enthalpy balance required over the heat exchanger, then we have to do energy balance or enthalpy balance over the heat exchanger, this heat exchanger, or by using a refrigerant. As in figure B, this one, enthalpy balance and mass balance required over the intercooler. Then we have to do an energy balance and mass balance over the intercooler. So normally this is used for any other system where we are compressing the air from let's say from ambient condition of 1.1 bar to 20 bar, and then using it in the industry for pneumatic devices. Then we use this kind of arrangement where we have a heat exchanger where cold water is served from the one pipe and the hot air is coming from here, and then it is getting cooler and then going to the high stage compression. But in case of our refrigerator system, we have a better thing to do. That is, we already had the flash tank installed. We already know that we need a flash tank to remove the flash gas. So we are now going to use that flash tank for doing intercooling. So how we do that? We take the lowest stage compressor vapor from here and then dip it inside the flash tank liquid. So that way the liquid will stay here and the vapor which is coming from low stage compressor will bubble out from here at a colder temperature. Okay, so that's the idea. So that colder vapor will go into the high stage compressor. So one of the design issues in multi-stage compression is the selection of a suitable intermediate pressure for air compressor with intercooling to the initial temperature. The theoretical work input to the system will be minimum when the pressure ratios are equal for all stages, and I have shown you that calculation how to do it. You simply take the differential of the work equation and equate it to 0, and then figure out what is the pressure equation. This also results in equal compressor discharge temperature for all compressors. Thus, for a two-stage compressor with intercooling, the optimum intermediate pressure for minimum total power is PI, that is intermediate pressure, is equal to the suction side pressure and the discharge side pressure. The suction side is the lowest stage compressor suction, and discharge is the high stage discharge of the compressor. So PI is the intercooler pressure, PS is the suction pressure of the low stage compressor, and PD is the discharge pressure of the high stage compressor. Low stage compressor, high stage compressor. So there will be a suction or discharge of this one, suction and discharge of this one. What we have, PS is the suction of the low stage one, this one, and PD is the discharge of the high pressure one, this one. PD is the discharge pressure of the high stage compressor in kilopascal. The above relation is found to hold good for ideal gases. For refrigerant correction, of course, we develop this equation, we develop all this work considering air, and we treat air as an ideal gas. But here we are dealing with refrigerant, so we have to apply a correction for it. For refrigerant, correction factors to the above equations are suggested, as the development of the equation does not consider the additional refrigerant compressed by the high stage compressor. So we have a complexity here. It is not just the whatever coming out of this low stage compressor is going into this high stage compressor. We have additional amount of vapor which is coming from here, which we have in flash gas removal, or the flash tank already has it. Okay, so that is why we have to apply a correction. In this scenario, whatever is coming out from this low stage compressor is going into the high stage compressor. But in our refrigerant situation, it is not the case. Whatever is coming from the low stage compressor, that is going to the high stage compressor, plus whatever gas we have separated in the flash tank. So it is more than that. So we have to apply a correction. But it does provide an approximate guideline for the optimal intermediate pressure. For refrigerant correction factor to the above equations are required. So the equation for the refrigerant will be PI is equal to PE PC multiplied by TC upon TE, where E stands for the evaporator and C for the condenser, and I is the intermediate pressure. Okay, so with this, using this equation, we can calculate what is the intermediate pressure for our refrigerant system. But most of the time in numerical, you will see that we will be using this equation, because this is rather easier to use than this one. So now we will be considering one by one different types of modification that we can do in our simple vapor compression system. So one situation will be two evaporator with single compressor, like this one here. We have two, whatever coming from the condenser is split into two portions, that goes into two evaporator, and we have only one compressor to compress back to the condenser. And of course we have to use a pressure reducing valve, PRV, for that one, for this one. So some applications require refrigerant at more than one temperature. As I said, the example of the dairy industry for the ice cream and the cold mill. 5 degree or minus 10 degree centigrade, separate throttling valve and separate compressor for each evaporator operating at different temperatures. System will be bulky and uneconomical. So instead of doing that, more practical and economical approach is to route all exit streams from the evaporator to a single compressor. A pressure reducing valve PRV is used to reduce the intermediate pressure to the compressor suction pressure. So we are using a PRV because of course this will be at a higher pressure and this will be a further lower pressure here. As you can see, this is the outlet of the condenser. So as it reaches 0.4, the pressure, the first evaporator is working at this pressure, which is at a higher pressure. So, and then we have compressor only at stage 1 here, at state 1 here. So we have to drop this high pressure vapor to this one. So reduce this pressure to pressure 6 or to pressure 1. We have to use a pressure reducing valve, that's here. And then the remaining refrigerant will go to state 7 right here to this through this expansion valve, and it will go to the lower stage evaporator and evaporate, produce some cooling effect here, and then it will come to state 1, and then both of these from first evaporator and the second evaporator will be compressed back to the condenser condition. So the mass balance, the mass flow rates are different in different parts of the cycle, hence both enthalpy and mass balance must be satisfied. If the PR is isenthalpic, then H5 should be equal to H6. If we are considering to be an isenthalpic one, then H5 should be equal to H6. It will be, we are just dropping the pressure but not changing anything else. But it is a irreversible process, so it is not isentropic. So, but it is, we are not adding any heat or anything to it, so it is, we call it that is isenthalpic process. So H5 will be equal to H6. So mass balance, if we do around this PRV, pressure reducing valve. So M6 plus M8, M6 is what is coming out from this line here, and M8 which is coming out from this line here. So initially 6 and 8 both are splitted from 0.3 and it is going to 0.1, which is leading to compressor. So M6, M dot 6 mass flow rate from 6 plus mass flow rate M dot 8 should be equal to the mass flow rate M dot 1 to the inlet of the compressor. That's the mass balance for the cycle. Energy balance after PRV or the inlet of the compressor. So we are doing energy balance across this PRV. So what is flowing into the PRV and what is leaving the PRV. Excuse me, sir. What is flowing into the PRV is M dot 6 and H6. So now this is leaving the PRV. Sorry, 6 and 8 are here and 1 is on there. So we are doing energy balance at point here. So M dot 6 H6 plus M dot 8 H8, what is coming into at point this here, and then it should be equal to what is leaving from here, which is M dot 1 H1. Energy balance after PRV or inlet of the compressor. So we are doing energy balance after PRV at this point. So what is flowing in at this point are M dot 8 and M dot 6 multiplied by their respective enthalpy, and what is leaving this point is M dot 1 multiplied by its enthalpy, M dot 1 multiplied by its enthalpy. So that's the energy balance at point after PRV, at a point after PRV. And COP of the total system will be equal to the cooling produced in the low pressure evaporator or QL1 and Q dot L2. So L1 and L2 divided by only one compressor watt divided by the one compressor watt. So M dot 8 H8 minus H7, H8 minus H7 is the refrigerating effect produced by this low temperature evaporator, plus M dot 5 into H5 minus H4 will be the refrigeration produced by this evaporator, divided by the work required by the compressor, which is m dot H2 minus H1, m dot H2 minus H1, and m dot 5 is equal to m dot 6. So if you can figure out, because we will be able to find out properties of 5 easily as compared to 6, so m dot 5 will be equal to m dot 6. m dot 5 is on saturated vapor line. So that's the energy balance for a 2 evaporator with single compressor system. We have to do the similar energy balance and mass balance for other types of combination. So this is an example of for a 2 evaporator 1 compressor system. We will be discussing it in the next lecture, inshallah.